These are the 8.3 notes, inverse trigonometric functions. This is page 4. So we want to make sure that we realize even though the inverse sign undoes the sign, it doesn't always return what we started with. So we want to take a look at some of how these can play out. Okay, first one is going to work the way we want. We are going to take a look at what we got on the inside here. I have got something a little deeper. Sine of pi over 4. Pi over 4 is in quadrant 1, so this is going to be positive. The sine of any multiple of pi over 4 is always square root of 2 over 2. Quadrant 1, so it's positive. So now we're looking for the inverse sine of square root of 2 over 2. First quadrant, we get pi over 4. That works the way we think it should. So B, I want the inverse sine of the sine of 3 pi over 4. So the sine of 3 pi over 4, 3 pi over 4 is in quadrant 2. So the sign here is still positive, positive square root of 2 over 2. But now I have to think about the restrictions on the range. The inverse sine of square root of 2 over 2 is pi over 4. So in this case, we do not return what we started with. C, I want the cosine of 2 pi over 3. That's in quadrant 2. Cosine is negative, so the cosine of 2 pi over 3 is negative 1/2. So now I'm looking for the inverse cosine of negative 1/2. And that is a quadrant 2 angle. Inverse cosine spits out angles in quadrant 1 and quadrant 2, so this does actually return 2 pi over 3. D, I want the inverse cosine of the cosine of negative pi over 3. Negative pi over 3 is in quadrant 4. And so my cosine there is positive 1/2. Cosine of negative pi over 3 is positive 1/2. I now want the inverse cosine of positive 1/2. This is going to return an angle in quadrant 1, and that's going to be positive pi over 3. Okay. Example 8, just a little more involved. I got the cosine of 13 pi over 6. First thing I'm going to do is rewrite that as the cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So now I'm looking for totally different things. Now I want the inverse sine of square root of 3 over 2. And that's actually the angle pi over 3. B, I want the inverse cosine of the sine of 11 pi over 4. Again, I want that as an angle between 0 and 2 pi. 8 pi over 4 is twice around the circle, so 11 pi over 4 minus 8 gives me a, sine of 3 pi over 4. Three pi over 4 is in quadrant 2. So the sine of that is actually still positive, square root of 2 over 2. I want the inverse cosine of square root of 2 over 2. That is positive in quadrant 1. Inverse cosine of square root of 2 over 2 is pi over 4. C is a little different. It wants the exact value for the cosine of the inverse tangent of 5 over 12. Now the problem is I don't know what the inverse tangent of 5 over 12 is. Those are both listed as positive. Could be quadrant 1, could be quadrant 3. But I know that tangent is opposite over adjacent. So I'm going to draw my reference triangle in here and put my theta right there. Opposite over adjacent, 5 over 12. Okay, so my opposite side is 5, my adjacent side is 12. I can now find the length of the hypotenuse. So I don't know what this value is. I am just calling it theta. Because I just need the placeholder. It doesn't really matter if I know what that angle is. In order to find the cosine of theta, I do need this hypotenuse. So I have got 5 squared plus 12 squared equals c squared. 25 plus 144. 169 is c squared. So the length of that is 13. So the cosine now is 12 over 13. So we are going to draw the reference triangle in. Figure out what the third side looks like and use that to find that trig value that we're being asked for. So I'm going to do the same thing with D. I have got inverse sine is 7/9. Sine is opposite over hypotenuse. So my opposite side is 7, my hypotenuse is 9. And here's my theta. Just a placeholder. So I want the cosine of theta, which means I need to find the length of the adjacent side. We're going to call that x squared plus 7 squared is 9 squared. X squared plus 49 equals 81. If we subtract 49 from both sides, I get x squared equals 32, which means x equals the square root of 32. If we're being asked to reduce, that's the square root of 16 times the square root of 2, or 4 square roots of 2. But my cosine, which is the length of the adjacent side over the length of the hypotenuse, is going to end up being 4 square roots of 2. That's the length of my adjacent side over the length of the hypotenuse, 9. Example 9 is going to be a little different because of this x over 3. No, it's not. Inverse sine. X is between -3 and 3, which makes the whole thing between -1 and 1. Okay, so sine is opposite over hypotenuse. Here's my hypotenuse. Here's my opposite side. Here's my theta. Sketchy part is now I have an x involved in this. So I want the cosine of theta. So let's see. I'm going to call this y for now. I got y squared plus x squared equals 3 squared. Y squared equals 9 minus x squared, because I don't know what x is. So y equals plus or minus the square root of 9 minus x. 9 minus x squared, sorry. And we're not even going to worry about the negative part right now. We're just going to focus on the positive. So this side now becomes the square root of 9 minus x squared. It's not pretty, but it'll make more sense and it'll be useful in calculus. So the cosine of theta is the length of the adjacent side, square root of 9 minus x squared, all over the hypotenuse, 3. And that's it. I need to know x before I can figure out what that is. But in the meantime, we do have an expression that works.